Precipitation Index for monitoring droughts.
Yeah, thanks. It's great to be back here at Purdue. I graduated from here in 2004. I'm thrilled to be here. Unfortunately, my fiance is not thrilled for me to be here. She's in Texas. I get married in 5 days. So she wasn't too happy with me taking this trip. Anyways, I should be able to catch us up here on time because my presentation isn't incredibly long. But here on the title slide, this is sort of an idea, a flavor of what's going on here in Texas. I got this picture offline from the Texas AgriLife website. This is supposed to be a pond for hundreds of cattle to water, or to get water out of. And I assume at some point it was much bigger than that, but I'm going to talk about this new SPI that we've developed in the State Climate Office and sort of give you a flavor of what's going on with the drought in Texas as well at the same time. So it's sort of two presentations kind of blended into one. Now, we have a need for drought monitoring in Texas. The main reason is we're a big state. At some point, or at any given time, we likely have drought conditions somewhere. Unfortunately, right now, we seem to have drought conditions everywhere. The picture is the latest U.S. drought monitor, and I believe this is a record for Texas. We have 64% of the state, or over 64% of the state, in exceptional drought right now. So it's very bad, and this covers every one of the 10 climate divisions in Texas. So we have a saying in Texas: don't mess with Texas. You can apply that to drought. Don't mess with Texas drought. Now, it's important, the drought monitoring is important because precipitation in Texas, as I have written here, is sensitive to variations in ENSO, and it seems to be becoming more and more that way. For instance, the past 8 months, ending at the end of May 2011, was the driest 8-month period on record, and this coincided with the latest La Nina, and this is including all periods, not just, I think it's October to May. It includes all October to Mays. It includes every 8-month period you can think of. So it's been extremely dry, needless to say. And drought is especially important in Texas because agriculture and water supply are particularly important. Most places in Texas, the water supply comes from a local source, so you can get a gauge of how water is doing just by looking at how you're doing drought-wise. So we have a need for drought monitoring. Now we need a need for higher resolution drought monitoring, and that's sort of what I'm going to talk about in regards to the modification of the SPI, the traditional SPI. And the reason this is important is because drought aid is given at the county level, and the U.S. Drought Monitor, which is a great tool for designating drought in a given area, wasn't originally designed to do this on the county and sub-county scale. So we really wanted to, in the State Climate Office, provide an improvement on this. Some of the traditional indices that are used for drought monitoring are at the climate division scale, where we have a good detailed record going back to 1895. So it's good to get a perspective of how things are going at any given time based on historical data. But as you can see, we only have 10 climate divisions in Texas. They're quite large. We have a big state. And something such as the Palmer Drought Index a lot of times doesn't give a great idea of what is going on. For instance, this is long-term conditions. September 2009, South Central Texas, we're looking at extreme drought, and just 1 month later, in October 2009, completely gone. Now, I don't think that's quite an accurate picture. So this is just sort of an idea of why we wanted to improve drought monitoring as far as spatial resolution. Now we're going to take advantage of two high-resolution precipitation analyses that are available. The first one, I believe it was mentioned a little bit earlier, are the multi-sensor precipitation estimates. These are provided on a daily basis by the river forecast centers as part of the National Weather Service. There's a lot of acronyms in there. So the NWS, MPE, provided by the RFC, a little bit of acronym soup for you there. Anyhow, these are provided on a daily basis. And the picture I'm showing here isn't necessarily daily precipitation. It would be nice if we could get a day with this much precipitation. We sure could use it. But this is aggregated over the month of May. So we have this precipitation data available on a daily basis. Unfortunately, it only goes back to 2005. So we need some sort of historical perspective to put this into. And one of the things we do is utilize the PRISM climatology. The folks at Oregon State University provide this, I believe, at a 1 kilometer resolution, while this is available at the 4 kilometer resolution. So we have these two tools available, these high resolution analyses, one a normal product and one a daily precipitation product. The issue that we have is putting this precipitation data that we have available on a daily basis, which is nice, putting it in a historical perspective. Now, it'd be nice if we had high resolution data going back several years, but we don't. But the solution to this is to utilize the fairly dense co-op network that we have in Texas. Now, we're looking for stations that have long-term data, so reliable stations is what we're looking at. And there's a picture of what we have in Texas. I'm not going to dive into the specifics of it, but basically what we want to do is cluster these stations together so that we get stations with similar precipitation characteristics, and then we perform what's called a regional frequency analysis. Now, I'll be honest with you, this is largely based on the work of Hosking and Wallace, and without this I'd be lost, and none of this would be possible. So major thanks to them. But what we do is basically calculate L moment ratios. Now these are simplified statistics for each station. I'm not a statistician, so I'm not going to go into any great detail about what happens because I'd get lost trying to explain it to you. But basically at each station we compute L moment ratios. And what's useful about L moment ratios is these are normalized. I'll dive into that a little bit, maybe on the next slide. But basically, we have these at the stations, and then we interpolate these at the 4 kilometer grid. And this is based on the historical data. So we have a historical distribution, and these L moment ratios are transformed to a Pearson type 3 distribution. So we have the historical distributions, and these are all normalized. So each one has a mean of 1. So here's a little teaser of the sort of product that we developed at the Texas State Climate Office. High resolution, and what we're looking at is this past week is 2-month percent of normal. This gives you an idea that on the short term, other than the extreme northeastern part of the state, we're very dry. But anyways, the percent of normal is this aggregated or accumulated multi-sensor precipitation estimate divided by the PRISM normal. So that's how we use those two high resolution tools. We can get a percent of normal. And as I mentioned with the L moment ratios, at each station and each grid point, the mean is 1. So here's another product we put out. This is the traditional SPI. And the SPI is basically the number of standard deviations you are above or below a mean. And of course, since it's standardized, the mean is 0. It's not 1. So basically a negative number means you're below average, positive number above average. That's one of the strengths of the SPI. Perhaps the main one, and you could look at this as either a strength or a weakness of the SPI, is that it includes only precipitation data. It only includes precipitation data. That makes it very easy. But again, you're not considering temperature, evapotranspiration, or other effects that may play in the drought. It's very easy to interpret. Normal precipitation, you have an SPI of 0. Negative value of SPI, drier than normal. As I wrote here, more negative value of SPI, the more negative value you get, the more drier you are. I know that's not correct English, but that's really the easiest way to explain it. And the nice thing about the SPI is that it's normalized to give a local perspective of dryness. And this is important in Texas because we have a huge variation in precipitation climate. And I just included an example here. El Paso, we average 9.43 inches. Beaumont, about 6 times that amount for a given year. And those of you familiar with the SPI know that you can calculate it over a number of different time intervals. So you can determine wetness and dryness on different scales. Now, one thing that this modified, and I want to call it modified, not necessarily an improved SPI product, looks at a shortcoming of the traditional SPI Dr. Nielsen Gammon and I found was that it really weights any precipitation amount that you have within a given period equally. So the modification that we're going to make, fairly simple to understand, is that we're going to use differential weighting of precipitation for a given accumulation period. So succinctly, give greater weight to more recent precipitation, less weight to less recent precipitation. Again, I don't know if that's correct English, but moving on. So you can think of it as the SPI blend as an integration of precipitation over time. Go ahead and use an example here. This is accumulated precipitation in San Antonio for 4 notable droughts. This is all ending in July. The most recent drought that we had, other than the one that's ongoing right now, was in 2009. And this is going back in time. So this is starting in July 2009 and heading back in time, the amount of precipitation that we had. And what I want to point out here is if you look at the 30-month accumulated precip in San Antonio for the 1996 drought and the 2009 drought, it looks relatively similar. But if you take the area under the curve leading up to the 30-month accumulation, you notice that there's much more area underneath the 1996 curve than there is the 2009 curve. Hence, you had much more precipitation during the 2009 episode further back in time, whereas in 1996, precipitation was more recent. So that's sort of what we're dealing with on at a mathematical perspective here. Now this slide is kind of busy, so I don't know whether to just skip over it because it's sort of a simplification. Just given a scenario, you have 3-month SPI. Basically, you have 2 different years. You're looking at the same station, so the same climatology. Both years, you end up with 3-month total being 18 inches. The only difference is in year 1, the rainfall fell further back in time in June than it did in year 2. So the traditional SPI said that you have a normal each month of 5 inches, which is reasonable in Texas, well, in some parts of Texas. So traditional SPI, both years, you have 120% of normal. So your SPI value would be the same. Whereas with the SPI blend, which is what we came up with, you can think of it, if you wanted to use your weighting in terms of linear decrease of weights going back in time. Year 1, you provide more weight to the August precipitation total, and you do that for both years. And what you end up with, when you calculate the normal in the same manner, you end up with 97% of normal in year 1 and much above normal in year 2, which makes sense because of the precipitation, the heavy precipitation fell more recently. So here's an overview. And the SPI blend is more of a concept. I guess that's what I want to kind of get across than an actual set algorithm. We designed several SPI blends that we think fit well in Texas, but really it's just differential weighting of your precipitation amounts within a period, I guess, is how we define an SPI blend. So you need your PRISM normals, your co-op data, and your MPE data. So what we do with our SPI blend products is we calculate that percent of normal, and then we find where it lies on a cumulative distribution function, which again comes from the co-op data that is interpolated, I don't know what's going on there, to a high resolution grid. And then what we do with our product, since it's designed for use with the US Drought Monitor, we assign categories, the drought level, the D level categories, based on the percentile that it falls in the CDF. And this down here, this is just me being silly. We have 46,000 grid points in Texas. Just to explain what an increase this is in the amount of information that we get instead of 10 climate divisions. Indiana only has 6,000, so again, everything's bigger in Texas. So here's the current products that we put out, and we do the weighting for we have what's called a 2-month blend, and the naming is sort of confusing With the 2-month blend, we weight daily precipitation data. With the rest of the blends that we put out, SPI blends, we weight precipitation on a monthly basis. So what you do, I think I have a figure after this that explains how the weighting works. So it's just a simple, with our 2-month SPI blend, just have a simple linear decrease in the weights for each day as we go back in time. What's shown on the bottom is the 24-month SPI blend that we put out, and that's to look more at long-term rainfall. And going back to this, very simple. We just add the 12-month precipitation total plus the 13-month precipitation total on and on until we get out to 36 months. You know, notice that 24 months lies right in the middle there. So this is what you get when you do the weighting that way. You weight the most recent 12-month precipitation equally, and then you have a linear decrease, and you eventually get to 0 once you reach 36 months. So again, I mentioned you place the current data on a historical CDF, the current MPE data on the CDF based on the co-op data, co-op station data, and then based on the percentile, what we output are maps that show U.S. drought monitor categories. So it can be directly related to the U.S. drought monitor. And here's an explanation of the categories. Anytime you're less than the second percentile, that's when you get exceptional drought. So 98% of the time, you expect not to be an exceptional drought in a given location. And as we'll see coming up, that's certainly not the case in Texas. Now this is where I provide a nice look at the sort of maps that we produce, and sort of giving an overview of how, for lack of a better word, depressing it is in Texas right now. This is the blend, or this is the products that we ran last week. We run them on a weekly basis to coincide with the U.S. drought monitor so that we can provide high resolution input to Texas. And as you can see, there's a lot of exceptional drought. I'm not sure how well the colors are showing up, but if you take my word for it, the darkest color is spread throughout most of Texas. The only areas that receive appreciable rainfall over the springtime was the Dallas-Fort Worth area and towards the northeast. This is sort of comparing it to the traditional SPI, and we include this on our website because it does give some good information. It's nice to have the SPI values as opposed to just these sort of subjective categories, but it actually matches up quite well in terms of showing exceptional drought, which with the SPI is below -2.0, and if you have an SPI below -1, you're looking at the 15th percentile, which would be indicative of at least severe drought. So anyhow, moving on, this is an example of where I believe the SPI blend provides an improvement over the SPI. This is our 2-month SPI at the top, November 2nd, 1 week later on November 9th. And what you see in central Texas is the path of Tropical Storm Hermine, which dumped excessive rainfall. It sort of went up through the middle of Texas, dumped some significant rainfall in the Austin area and up towards Dallas-Fort Worth. What you see is the artifact of the SPI not giving an equal weighting to precipitation amounts. 1 week later, the 2-month SPI goes basically from above normal rainfall to exceptional drought. Whereas the 2-month SPI blend, which weights more recent rainfall, doesn't show that dramatic transition between non-drought and drought. 6-month SPI blend, this includes data from past 8 months, anywhere from 6 months to 12 months. The driest 8-month period, as I mentioned earlier, devastating to agriculture. 12-month, looking more towards East Texas. And even on this, you can see the path of Tropical Storm Hermine, which is basically the only reason that this area of central and north central Texas, at 12 months, isn't experiencing exceptional drought. But this gives you an idea that you can look at drought on several different levels. Definitely the drought is much more severe across all of Texas at shorter term than some of the longer term blends. Here's 18 months. And you notice that East Texas is particularly dry, 24 months. This is where we start getting issues with the actual input precipitation data. We have some discontinuities between these radars. We actually don't get any data out here in West Texas because of the Davis Mountains. But you do start to see some discontinuities showing up, and that's an issue that we're trying to work out, which we're confident we can do over the next couple of years. Here is our total SPI blend, which looks at 1 month plus 2 months, all the way up to 36 months. So it looks at both short-term and long-term drought. And I pointed out where College Station is at. That's where A&M is located, right here, right in the middle of this exceptional drought area. I can vouch for you that it's bad there. Minimum SPI blend. This is a fun product, especially now, because it takes whatever period of time the drought is the most severe at and just plots that value. So at some time, or at any time, I'm not saying that very well. Most of Texas, at least one time scale, is experiencing exceptional drought. So here's a summary. Droughts are frequent in Texas. That provided the motivation for this product. Not only the creation of a higher resolution product, but also the development of an SPI blend, which is what we call it. Future work, we'll be expanding this out from Texas to the eastern 2/3 of the United States, teaming up with North Carolina State and Purdue. Dev is gonna team up with us on this. And there may be, in the future, some tweaking of these blends to incorporate daily data on all of the time scales instead of using monthly data. And here, the products are available online. Here's the website right there. Thanks. Boiler up and gig 'em. That's it.
Any questions for Brent?
You mentioned about using daily data for all time scales. Is just the massive computational
Yep.
issues now?
Exactly. Yeah. Yeah, it would be nicer because we still do get some slight discontinuities like you do with the SPI. Yeah, Mark.
Obviously, I like this concept. I have a question. At one point, you only showed an example of going back 3 months. Let's say we go back 6 months or 9 months. Is that multiplication factor times 6 or 9? Or what point does that level off? Because my question is,
Yeah.
from a groundwater perspective, or let's say in my part of the country, from a soil recharge perspective, if we get 100% soil recharge, we're much less reliant on spring rainfall. We might need timely rainfall during certain, phenological state. But getting that soil moisture totally recharged is important. What happened back in the fall,
Yep.
6 months ago. So I'm wondering if this could be looked at sort of almost regionally or seasonally. Take some of that into account. It might complicate things. But
Yeah. Well, that's.
How far back do you multiply this factor before that? How far you go back before you don't count it really?
Yeah. Basically, what you do is the 2 month, each, I guess, timestamp that we assign to it is basically the middle. So, say for the 12 months, we look 9 months out and plus.
The third sort of then?
Yeah. But as I mentioned, this is sort of a concept.
Yeah.
So really, it's just an idea of you can really weight things however you want to. So yeah, I'd definitely be open.
Looking at terciles, the 4, 8, and 12, right? Or 18,
Yeah.
6, 12, and 8.
Yeah, definitely. Yeah, we may be doing overkill by doing every single month. Yeah, go ahead.
In the introduction of the SPI method, you give example where for year 1 you would weight 10, while for year 2 you would weight 2. Normal weight is Y. So my question is, how do you determine this weight? Like for year 1, if the weight plus 8 or 11, so I'm interested how you determine this weight in the
Yeah. So this is the slide you're talking about. So this is just a simple example. As I mentioned, the SPI blend is a concept. So this is just a simple example. What I do here, you want to weight August more recent or more heavily because it's more recent. The theory being that more recent precipitation will have a greater effect on drought than less recent. This year 1 and year 2 is just, I hope that's not confusing. You could think of this as, say, 1998, and this is 2009. It's just two different examples. Does that clear anything up? Did I confuse you more? I'm sorry. I don't know if I did a great job explaining that. But really, you could weight this like 1.2. You could weight this as 1. It's, as I mentioned, it's just a concept. It's in the sort of the infant stages as far as development and sophistication level of the products that we have. So I'd be open to input if you have any good ideas for weighting. Any other questions? Sure.
There is this normalizing with respect to spatial resolution. Could you give us some clues as to how you normalize it within? You have increased the resolution, you said.
Mm-hmm.
How did you normalize it? And what about the data points? How did you get that data within that resolution?
Okay, so the
Are the stations available for you to get that kind of information?
Yeah, what we have here are all the stations that were used, that were interpolated to the same grid that we get for the MPE. So all of the statistics per se, which I don't know a whole lot about, I sort of relied heavily upon this, and they wrote a series of programs that really helped me out. So I'm not a statistician, but the main idea of that is that you get L moment ratios, which are normalized so that at each station you get a mean of 1. So that way you can extract or interpolate that to a grid without having to worry about what the normal rainfall is. So what we do with that's why we extrapolate. You start to get different higher order parameters that determine the shape and the skewness as opposed to the mean. And then once they're interpolated, we use the PRISM data to provide what the mean value is. So basically every time we're calculating a percent of normal, which is just whatever the input is, whatever the precipitation input is at real time based on the climatology. I hope that answered that.
All right, one last question now.
Yeah, so there have been climatologies built around each radar, and that's something that the RFCs probably have. So you might be able to take out some of the attenuation and blocking, and of course, frozen precipitation is worthless on them.
Yeah.
So as far as amounts, it's not such a big issue in Texas. You're fine down there, but even north, it's much more of an issue.
Yeah. Mm-hmm. Yeah.
There's a lot of, I'm scared using MPE climatologically. It's hard.
Well,
Okay?
yeah, that's the idea of using the PRISM is that
Yeah.
we don't really have a climatology. That's just providing the input at a given time. So the climatology is based on co-op stations to provide the distributions at the grid points, with a mean of 1, I believe, maybe a mean of 0. I'm not sure. Anyhow, and then we use PRISM to normalize the real-time data that we get, and then we plug that into the distribution to see how we're doing. But I've noticed that the estimates have gotten, there have been far fewer discontinuities between the radars recently. That's something that's improved since we started doing this.
The other thing is that we figure out a new phase array nukes, sort of climatology to start over.
Yeah, yeah, 81 to 2010. Okay,
Well,
thank.
let's thank Brent again for coming all the way from Texas and congratulate him on his impending marriage. Right?
Thanks. Appreciate it.